All right, welcome everyone. So in the previous video, we talked about having a matrix in a special form, reduced row echelon form, and why putting a matrix into that form would be particularly useful when we're trying to solve a system of linear equations. So in this video, I want to talk about a systematic way that we can develop an algorithm that will guarantee, given any matrix, if I follow these steps, here's how I can express it equivalently in reduced row echelon form. So to motivate this example, this algorithm, let's imagine we're working with this following matrix over here. And we'll assume that this matrix is an augmented matrix of some system of linear equations. And our goal is to solve this system of linear equations. And so therefore, our goal is going to be to take this matrix, use some elementary row operations, and express it in an equivalent form, which is in reduced row echelon form. So the first step here is we are going to begin with the leftmost non-zero column. We're going to call this the pivot column. And since our leftmost column over here has non-zero entries in it, this is our pivot column. If I had a matrix that the first column were all zeros, then the pivot column I would go to the right and keep going to the right until I reach a column where there is some non-zero entry in that column. So our pivot column has a 0 in the top row. The next step is going to be, let's make sure that our pivot column has a non-zero entry way in the top row. And so that is not the case here, but I could easily interchange a couple of rows so that suddenly now the pivot column has a non-zero entry way on the top. And I can do this in 3 different ways. I can interchange row 1 and row 2, and then I would have a -1 up here. I can interchange row 3 and row 1, or I can interchange row 4 with row 1. And since it's going to be nice to have leading entries equal to 1, maybe it'll save me a little bit of time if I switch row 1 with row 4, and then I'll have a 1 up here in this spot. But keep in mind, as I go through this process, it's not a unique way of following the flow here. There are different ways that I could get a non-zero entry in the top row. But I'm going to interchange row 4 with row 1, and now I've highlighted the pivot in this first pivot column. So I'm going to call this entry 1 on the top row as my pivot in the first column. Okay, so far, just by doing an interchanging of rows, we have our first pivot column, which is the leftmost column, and now we have a pivot in the top row, which happens to be 1. And what we want, if we're going to get a row echelon form, is below each of these leading entries, we're now calling them pivots, should be all 0 terms. So I should have a 0 here, and I should have a 0 over here. So the way that we get zeros is going to be by using the replacement operation. I'm going to, for example, add 1 times this row to this row, and that's going to eliminate the 1 over here. And I could similarly do a replacement operation to clear out the non-zero entry here in order to make that a 0. So in this case, we do 2 replacement operations on row 2 and on row 3. And now we have our first pivot column, which has the very top entry non-zero, and all of the entries below it are equal to 0. And now what's left is inside here, we have what we're going to call a submatrix. So this is now a smaller matrix embedded inside of this larger matrix. And now we're going to do a similar process on this submatrix. Okay, so now we are going to just focus on the submatrix that I've boxed in red. So we ignore this top row. It already has a leading entry over here and has zeros below it. So now we do the same thing on this submatrix that we just did. In other words, I'm going to pick my pivot column, and since this first column on the leftmost column has non-zero entries, that's my pivot column. Then I pick a pivot entry, and so the top entry here is already non-zero. So I'm going to pick 2 as my pivot. And then after I have my pivot, the goal is going to be to use replacement. So I'm going to use this row and replacement to get zeros below each of these leading entries. So for example, I can multiply this row by minus 5/2 and add it to this row to eliminate the 5. And if you do that, what you'll actually see is we get a 0 here, we get a 0 here, and we get a 0 over here. So after doing those two steps on the submatrix that I've boxed in over here, this would be the result. And so notice now I have an entire row of zeros. So now I can ignore the top two rows and I have this submatrix to work with, and I do the same two steps on this submatrix. And so since this submatrix has a row of zeros, I want to make sure that any row that has that these rows of zeros should be the bottom rows. So I'm going to do an interchange of row 3 and row 4. And now I have the matrix in what we called row echelon form. This is not reduced row echelon form because these leading entries are not equal to 1, and we don't have zeros above those leading entries. But we have this currently in what we called row echelon form. And so on the next slide, we're going to add 2 additional steps that are going to complete the process to write this in reduced row echelon form. Okay, so far we've got this original matrix. We did some elementary row operations, and now we have it in row echelon form. And we want to get it into reduced row echelon form. So one of the conditions is that each of these leading entries, so notice here on the top row, my leading entry is a 1. I'm going to call this a pivot. In row 2, our pivot is the first non-zero entry, which is the 2 over here in column 2. And then in row 3, our first pivot would be located over here. In the 4th column is the -5. And then our last row does not have any pivot because it is a row of all zeros. So in order to satisfy the condition that each row should have a pivot which is equal to 1, we can just scale each of these rows. So the top row already satisfies this condition. Let me scale this. I'm going to multiply row 2 by 1/2, and I'm going to multiply row 3 by -1/5. And so now we are one step closer to putting this in reduced row echelon form. What's left is we want to, above each of these pivots should be all 0. So this is not a 0. Here's my other pivot. And I also should have zeros over here. So next up is going to be to fix that part of the puzzle. So I'm going to begin with the rightmost pivot. So that's this one right over here. And I'm going to use replacement to make these entries above it 0. So for example, I can make this one 0 by multiplying this row by 3 and adding it to the row above it. And I can make this one 0 by multiplying this row by 9 and adding it to row 1. So doing those 2 replacements, we are one step closer. So now we have zeros above that rightmost pivot. Then we repeat going over to the next pivot. So now we use this pivot of 1, and I want to make this 0 above it. So I can multiply this row by -4, add it to the row above it to replace the top row. And now we have the matrix in reduced row echelon form. Each of our pivots is now a 1, and not only are the entries below each pivot 0, but now we also have the entries above each pivot are also 0. And if we return back to the context of solving systems of linear equations, we have seen why having a matrix in this form, equivalent form, is going to be much easier to read the solutions from a matrix in this form as opposed to the really complicated looking matrix that we started with. So on the next slide, I just want to summarize this process before we take a look at some examples. Okay, so this slide, I just want to summarize the steps that we just applied in the previous example. So by following this process, no matter how big our matrix that we start with, we'll be able to express that matrix in reduced row echelon form. It just may take us a lot of steps to do so. But to recap what we did, we first identify the pivot column, and this is the leftmost column that has a non-zero entry in it. Then we possibly had to do some interchanging to make sure that the non-zero entry that appears in that pivot column appears in the top row of that column. So that might be doing some interchanges. Then we use row replacement to create all zeros in all positions below the pivot. And then we repeated this on each of the sub matrices. And at this stage of the process, this is when the matrix was in row echelon form. Then we can scale each of the rows so that our leading entry, the pivot in that row, is equal to 1. And then the last thing that we wanted to do was to go ahead and then replace all of the entries above each pivot. So we want to use a replacement so that all of the entries above each pivot are also 0. And so by following these steps, we've got a foolproof plan for doing that. And we call this process Gaussian elimination off of the mathematician Carl Gauss, who pretty much has done everything. And so we call this process Gaussian elimination. It is also called row reduction. So by following that Gaussian elimination process, we have proven that given any matrix, there are a series of elementary row operations that we can apply to that matrix that will write it in an equivalent reduced row echelon form. So RREF, reduced row echelon form. Sometimes we abbreviate that with RREF. So here is an example of a 3x3 matrix where we've performed these operations and put it into reduced row echelon form over here. So for any matrix, we can do this. The thing that you want to be aware of is that the process, even though we follow this process, there might not be a unique way of doing that. For example, we can decide in our pivot column on the left which of these entries we would like to make the pivot. So I could replace row 1, interchange row 1 and row 2, and go about it in that way. I could very easily have done it this way as well. Interchange row 1 with row 3 first and followed through this process. And no matter how you do it, in the end, the reduced row echelon form will be the same. So not only does the reduced row echelon form exist for each matrix, but that form is unique. So here is a theorem. I'm not going to prove it, but hopefully this example gives you a little bit of a gist for why this might be true. So given any matrix, it is going to be equivalent to 1 and exactly 1 reduced row echelon matrix. Okay, so that wraps up the main idea of this section. In the next couple of videos, going to work through some examples to see how we can identify what type of solution, consistent, inconsistent, we might have based on the form of the reduced row echelon matrix.